In this lesson, we'll apply what we have learned about logarithms and exponentials as well in order to solve exponential and log equations. And the very first thing we will look at is when we have something, an equation that is in exponential form, such as you see in classroom example 1, look at what that property is that is listed above. What you will notice is there are no logs in this equation at the beginning. So if you look at it and it's an exponential form and there's no way to rewrite bases to be the same value, there's not a number that I can rewrite 8 and 21 as with the same base raised to a power. It just doesn't exist. That's not possible. So what I can do is apply the property that as long as I do the same thing to both sides, I will get something that is equivalent. Therefore, watch what happens if we decide to take the log of each side. So in this example, we'll start by taking the log of 8 to the x power is equal to the log of 21. And you can choose whether you want to use common log or you want to use natural log. It doesn't matter here. By using the common log, I know I've created base 10 logarithms. But if I think about the properties that I know I can use with logs, what can I do with this exponent that's on the 8? Well, remember, it pulls down in front and becomes x times log 8 equals log 21. Now we can solve for x. If we divide each side by log 8, we isolate for x, and what you will find if you put this into your calculator, you can type in parentheses log 21, divide, close your parentheses, then do divided by, in another parentheses, put log 8. You want to be sure you put the parentheses around it so the calculator will recognize that it does order of operations the way that you intend. And if we round to the nearest thousandth, as the instruction told us to do, we would get 1.464. Now, we need to go back and make sure this seems reasonable. If we look at the original equation we had, 8 raised to what power would give us 21? Well, I know 8 to the first power is just 8, but if I put in 2 for x, 8 squared is 64. So obviously, it has to be a number between 1 and 2, and 1.464 is a logical, reasonable answer. And I could actually type in 8 and raise it to the 1.464 power. Remember, that was rounded, so it will not give us exactly 21, but it should give us something very close to 21. Now, we have a couple of other examples, but these involve values that have a base of e. So one thing we will want to pay attention to is when our base is e, I don't think we'll want to use a common log. We're going to want to use a natural log so that it will be using a base of e as well. That will make our cleanup easier. Now again, when I look at this equation on the left, e raised to the absolute value of x power is equal to 50. I don't know what the exponent would need to be on e in order to turn it into 50. So it's an exponential. I cannot rewrite 50 as a base that has e. So what I will need to do is to take the natural log of each side. Now you may be wondering about the absolute value around the x. We'll talk about it when we get to the end. For now, just don't drop it. Leave it there. Okay, on the left side, if I'm asking you what exponent does e, because remember the natural log automatically has an understood base of e, so it's saying what exponent would e have to be raised to in order to get back e to the absolute value of x power? Well, if you remember from earlier lessons, it will have to equal what the exponent already is when the base after the logarithm and the base that follows it match. So we're just going to simplify that to be the absolute value of x is equal to the natural log of 50. And that's something that's ready to go directly into our calculator. Now this is why the absolute value is there. Could there be more than one value we could get for x? Because if I take the absolute value, I know that means I'm going to take the positive of whatever is in there. So when I pull this value out of my calculator and I round it to 3 decimal places, I should have 3.912, but by removing those absolute value bars, I would need to say I could use either a positive or a negative of that number, because if I put the negative into the absolute value bars, it will still turn it back into a positive. So there are 2 different values we can use for x on that one. Now when you look at b, again, I don't see any logs anywhere, so that tends to make me think I will probably want to take the log of each side, but notice I do not have a single base. On the left side, I have a product that has like bases. Well, I do know a rule for working with exponents if I'm multiplying and the bases are the same. I need to add the exponents and then I can write it with a single base. So that means I have e raised to the 4x plus x minus 1 power, and that is equal to 5e on the other side. Now that I have something raised to a power on the left is equal to something on the right, I'm ready to take the logarithm, and again, because it is base e, I want to take the natural log. And if I add together those exponents, we will have the natural log of e to the 5x minus 1 power on the left is equal to the natural log of 5e on the right, but be very careful. I'm taking the natural log of that entire side. Be sure you put the 5e in parentheses. That's important because notice that's a product, 5 times e. I'm going to have to use that product rule that we learned with logarithms and separate that into the natural log of 5 plus the natural log of e. I really can't do anything with it if I leave it as the natural log of 5 times e. I've got to separate it out to evaluate. Now on the left side, the natural log of e to the 5x minus 1 power can be simplified because that's saying e raised to what power would give me e to the 5x minus 1 power. Therefore, it simplifies to be just whatever that exponent is, which is 5x minus 1. Now, let's clean up. We're trying to solve for x, so add 1 to each side. And here's what we have. 5x on the left is equal to, now the natural log of 5, I can put that in the calculator, and I'll do that in a moment. But what happens if I evaluate the natural log of e? That's asking e raised to what power will give you e to the first power as your answer. The natural log of e is just 1. And if I add 1 plus 1, I will get 2. So I have 5x equals the natural log of 5 plus 2. We're almost there. The last step to get x isolated is to divide by 5. And remember, I'm dividing that entire right side by 5. So it's time to go to the calculator. It tells me to give my solution to the nearest thousandth. When I do that, I will get x is equal to 0.722. And that would be my solution. As we move to the next page, we're going to notice that these equations look just a little different. One thing you should see is that on these, there are logs only on one side, not two. But there is a log here now. The ones we just looked at didn't have any logs to begin with. So what we want to do, if something is written in log form, we want to change it to exponential form, and then hopefully it will be something we can solve. Most of us do not think in terms of logarithms, but we could work a little more effectively in exponential form if we make that adjustment. So let's look at A. What I notice is there is a log, but it's only on one side. It's also being multiplied times 4. So I'm going to isolate that natural log by dividing each side by 4. Now, when I do that, that tells me that the natural log of x is equal to 9. Now, I have no idea what number I need so that when I take the natural log of it, I get 9. But what I do know is that the base on a natural log is base e. And I can pull this back into exponential form if I write it as e has to be raised to the 9th power in order to equal x. And if I look at my instructions, it says give exact values. I'm done. E to the 9th is the exact number. I could put it in the calculator to get a decimal approximation, but this is not asking for that. It just wants the exact value. That's it. Now, if you look at example B, again, I see a log on one side, so I need to look at that and see if it's possible to put it back into exponential form. And I think I can do that because the base for this logarithm is 3 raised to the first power would equal x cubed minus 5. Now, that looks like something I might be able to work with. I'm trying to solve for x, so we want to isolate it. Let's add 5 to each side. 3 to the first power is just 3. If I add 5 to it, I get 8 is equal to x to the third power. So what I am asking for is what number can you cube to get 8? In other words, I'm going to take the cubed root of each side, or I'm going to raise each side to the 1/3 power, whichever way you want to think about it. If you want to put that in your calculator to simplify, you can, but we could also use prime factorization here. I know that the prime number 2 would divide into 8 4 times, and 2 will go into 4 2 more times. That's 3 of a kind. That's what I'm looking for when it asks for a cubed root. That means x would be equal to 2. 2 times 2 times 2 gives me 8. And again, I could plug that back into the original equation, and I would discover that, yes, I would end up with the left side equaling the right when I do that. Now, the last type of example is this one on classroom example 6, and I'm hoping what you notice is that we have a third type here. This is when you see logs on both sides. In fact, you might say this equation looks like there's logs everywhere. I had a student one time who said it looks like a forest. I see logs everywhere. When that's the case, you want to get a single log on each side. Notice on our left side, we have more than one log. So get a single log on each side, and then you can drop the logs. Here's the idea. If log this equals log that, the only way that's going to be true is if this equals that. In essence, we're still doing the same thing to each side. We're removing the logarithm from each side, and that's perfectly legal to do as long as we're doing exactly the same thing to each side. So if we look at this equation, think about your properties you know for logarithms. I have a log plus another log. That has been expanded. If I want to condense it, then I would rewrite this as the log of the product of 2x plus 1 times x. Remember, if we were adding exponents, that's because we were multiplying the bases. So if I see logarithms that are being added together, what I have to do is write it as a single log, but it's a product of what follows those bases. And that would equal, it's still just the log of the expression x plus 8 on the right side. Now I can do a little cleanup on the left because I can distribute the x times 2x plus 1. That would give me 2x squared plus x. So I have the log of that on the left is equal to the log of x plus 8 on the right. And now that it says log this equals log that, I can just drop the logs. And I have 2x squared plus x equals x plus 8. Well, I need to get my like terms together to try to solve. And I miswrote this. Let's correct what I did on the left. That's supposed to be 2x squared plus x is equal to x plus 8 on the right. So let's subtract x from each side. And I have 2x squared equals 8. And to isolate the x term, I will need to divide each side by 2. That means x squared equals 4. Now be careful using that square root property. If I take the square root of each side, you need to remember there's both a positive root and a negative root. I would get x is equal to positive 2 or negative 2 as my two possible solutions. But here's where we have to be careful. Remember what we talked about earlier in this chapter. We have some restrictions when we're working with logarithms, and that is that the domain values, what our x values can be, when I plug in what's following a logarithm has to be a positive number. And if I were to plug in negative 2 into either of these three logarithms, what I'm going to see is that gives me negative values after the logs. I cannot use the negative 2. I can only use the positive 2, which takes us to the next page, which gives us a reminder rule at the top. Recall that the domain of y equals log base a of x is not including 0. So it's a parenthesis 0 to infinity. And for this reason, it's always necessary to check that the proposed solution of a logarithmic equation results in logarithms of positive numbers in the original equation. If I try to plug back in for x and it would give me something negative after the base in the log expression, it's not valid. I can't use it. Now be careful on that. It doesn't mean that I can't use a negative value of x just because x is a negative value. It means whatever number I get, if I plug it in, I can't have a negative after the logarithm. Most of the time, if I get a positive number, I'm probably fine, but I should still always look just to make sure. If we look at this example, notice that there is a little bit of cleanup that can be done because I have 4x plus 1 times x plus 1 following log base 3 on the left. I can use FOIL and I can expand that, and I'm going to end up with log base 3 of, if you use FOIL or the box, you end up with 4x squared plus 5x plus 1, and that is set equal to 3. Now I need to pay attention. Do I see no logs, 1 log, or logs on both sides? Well, I see 1 log. My method for solving is to go back into exponential form. So this is saying the base of 3 has to be raised to the 3rd power in order to get back 4x squared plus 5x plus 1. So by taking it into exponential form, I can clean up on the left. 3 to the 3rd power is 27. And then I can subtract 27 from each side because I notice this is quadratic. I'm going to have to set it equal to 0. and that will give me 4x squared plus 5x. When I subtract 27 from 1, I get a negative 26. Now, at this point, if it factors, that's probably a faster way to solve. You could use the AC method. If you know another way to factor, perfectly okay. I'm just going to demonstrate what the factored form looks like here. We would end up with 4x times x to get 4x squared, and I would end up with a 4x plus 13 in the first parentheses and an x minus 2 in the second, and I could use FOIL to double check myself to see that yes, it really will be equivalent to that trinomial 4x squared plus 5x minus 26, which now gives me two simple equations to solve. So if I take 4x plus 13, set it equal to 0, or x minus 2 equals 0, the one on the right is simple. I know I get x equals 2 there. Now on the left, if I subtract 13 from each side, I have 4x equals negative 13, and then if I divide by 4, I do have a negative fraction here, negative 13 over 4. But before you decide, no, that can't really work, let's go back and look at this original equation. The only place we have x's is this one log expression here, and it's a product. I know as long as I'm using the 2, I won't have any issues. That will be fine. But check what happens if I use x equals negative 13 over 4. If I plug in negative 13 over 4 into this first parentheses, 4 times negative 13 over 4 is just going to be negative 13. Negative 13 plus 1 would give me a negative number. If I plug negative 13 over 4 into the second parentheses, that's also going to give me a negative number because negative 13 over 4 is negative 3 and 1/4. If I add 1 to it, I still have a negative number. What happens if I multiply a negative times the negative? It actually gives me back a positive. So in this case, even though I had a negative value for x, it's not excluded because if I plug it in, it will still give me a positive value after the logarithm. So that's an important thing to check. We are going to skip example 8. Similar, so we don't need to do it, but I want you to go down to example 9, and we're going to look at what happens with this base E log equation. Now, this is another one of those forest questions. I'm sort of seeing logs everywhere. Of course, these are the natural logs. And you might be wondering, what am I going to do with this first natural log? Because it's the natural log of E raised to the natural log of x power. The fact that there's a logarithm in the exponent, don't let that stress you out. Remember, it's still saying E has to be raised to what power in order to get E raised to the natural x power. Well, all I need is that exponent. It's just going to be the natural log of x. Then I have minus the natural log of x minus 4 in parentheses is equal to the natural log of 5. Now I still have more than just a single log on the left. I have two, and they are separated with a subtraction sign. Think about those log properties. That would mean I can put it back together as a single log, but instead of multiplying, I would have to divide. So that would be the natural log of x over x minus 4 on the left is equal to the natural log of 5 on the right. Since there's a log on each side, a single log on each side, I can now drop those logs, and I have a simple proportion here. X over x minus 4 is equal to 5, or if you want to, write it as 5 over 1. You can cross multiply to solve, or you can multiply each side by the common denominator, which would be x minus 4, whichever way you prefer to do it. And what we will end up with is x equals 5 times x minus 4 distributed becomes 5x minus 20. If I move the 5x to the left side, so I get the x's together on one side, leave the negative 20 on the right, x minus 5x is a negative 4x equals negative 20. And then I can divide each side by negative 4. And x would equal positive 5. And I can just double check. I do not see any place I would have had a problem, but this is what I want you to notice. I actually would have had to have a value greater than 4 for x for this to actually have a solution. If I had gotten x equals 1, even though it's a positive value, it wouldn't have worked because it would have given me a negative value in this particular logarithm when it would give me a negative value after the log. So that would keep it from being a solution. But we're good with x equals 5. So all we have to do is sum up these properties. That's on the next page. And here's what we should know. If we're trying to solve either exponential or logarithmic equations, we're going to look at the form of the equation. The first example we saw was when there were no logs. If it's already in exponential form, but you can't get the bases to match, then your solution is to take the log of each side. Remember, sometimes it's better to use the natural log. If my base is e, that would certainly make cleanup easier. But you can choose whether you use the common log or the natural log. Now, the second type of problem is where I see a log on one side. And if there's a log on one side, then we go back to exponential form. So here's what this looks like symbolically. If we were to take log base a of f of x equals b, it means a raised to the b power would equal f of x. So we're going to go back to exponential form. And I'll write that a raised to the b power would equal f of x, just so you can see what I mean by that. Third type is if I see logs on both sides. And if I see logs on both sides, and it has to be a single log on both sides, so sometimes, as we saw, we have to clean up first, then what happens is we drop the logs. And that means that if log base a of f of x is equal to log base a of g of x, we drop those logs, and it must be true that f of x equals g of x. If we have something that's a little more complicated, and by the way, this should be a dot instead of that box that you see there, if we have e raised to some power times e raised to another power, then we have to condense that and write it as a single expression before we apply any of these.